Welcome to NASA STEM EPDC Quick Bits Big Ideas in Science content. NASA STEM Engagement and Educator Professional Development Collaborative provides NASA resources and STEM strategies for STEM engagement. In this series, we intend to reach educators, parents, and caregivers to quickly explain a specific big idea in STEM. We will introduce a NASA example of how this idea is applied in the real world. And finally, we will demonstrate step-by-step how to lead this activity at home or in the classroom with your students. You might invite your students to watch with you at that time. We invite you to join us as we learn more from our specialists. Let's get started.
Hello, my name is Barbie Buckner, and I'm an education specialist at Goddard Space Flight Center in Greenbelt, Maryland. Today's big idea in science is about our solar system. In particular, we're going to highlight an activity for how you can make a solar system scroll. Students will use a strip of paper to construct a quick scale model of the distances between the orbits of the planets, the asteroid belt, and the Kuiper Belt, which is where Pluto is located. As students create their own personal scale model of our solar system, they will make comparisons regarding the distance between solar system objects and their own bodies, helping to make this activity personally relevant. Before we jump into the activity, let's talk about some of the questions that drive planetary science at NASA. Primarily, where did we come from, where are we going, and are we alone? As we look at these big questions, that leads us to talk about cosmic scale. And in talking about scale, we look at those in three different dimensions: time, size, and distance. Today, we'll talk about size and distance, and our activity will actually allow us to make a solar system scroll that deals with distance of the solar system to scale. When talking about size, it is important to remember that it is relative, and also that you need to have a proper scale such that you have the same ratio when comparing objects. For example, in this photo, an illustration of our solar system to scale created by the San Francisco-based artist Robert Zeich, this image features the sun in the background with the planets, our moon, and four dwarf planets lined up in the foreground in the relative scale of size to one another. Note that with this scale shown here, you can't see the entirety of the sun, and several of the objects are even a little difficult to see. So let's rescale, and in this image, we've removed the sun from comparison. It allows us to enlarge the planets so that we might be able to see them better. Here are our 8 planets of our solar system, as well as the dwarf planet Pluto. And as you can see that even at this scale, some of our smallest planets are still difficult to see. Common misconceptions about our solar system include the fact that planets are perceived to be much larger than they really are, that the distances to the planets are perceived to be much smaller than they really are, and that the orbits of the planets are perceived to be evenly spaced between the Sun and Pluto, and they're not. So while our activity today will focus on the scale of distance of our solar system, let's check out this JPL video on how big the planets are and how far away they are compared to each other. This will help give us a basis to better compare the sizes of planets and the distances between them.
Earth is a big place. If you could drive around the entire planet, it would take more than 16 days of non-stop driving at highway speeds. But compared to some of the planets in our solar system, it's pretty small. We often see planets displayed as similar in size, like this, to make details on smaller planets easier to see. In reality, the size of planets compared to each other looks more like this. Even though this shows the sizes of planets accurately, they aren't that close together. Because of the great distances between planets and the planet's relatively small sizes compared to those distances, it's practically impossible to create a visual representation on a screen or the page of a book that realistically represents the sizes of the planets and the distances between them. As a result, the best we can usually do is show the accurate sizes of the planets or the accurate distances between the planets. Remember, They aren't really lined up like this. In space, the planets' positions are constantly changing as they revolve around the sun.
So just to sum up what we saw in that video, as you can see on the top part of this, we've got the size to scale, but not the distance. And the bottom is distance to scale, but not the size. So it's a unique challenge in this universe in which we live. Today, we're going to look at solar system scroll and the scale of our universe for distance. In this activity, we'll fold a long strip of paper in different ways to show us where various objects within our solar system are relative to each other. The materials we'll need for this activity are a roll of adding machine tape, also called register tape, about 2 inches wide. You can also use a continuous roll of paper towels, pencils, fine tip Sharpies, or markers. Optional materials include colored pencils or crayons if you'd like to add drawings to your scroll, and scissors if you choose to cut the scroll rather than tear it. First, we need to determine how long our scroll is. The length should be about the size of your arm span. Arm span and reach is a physical measurement of the length from one end of your arms, measured at the fingertips, to the other when raised parallel to the ground at shoulder height at a 90-degree angle. For this activity, students need to be at least 5 feet tall to use their own arm span. If they are not 5 feet tall, allow them to work in pairs, such that 2 students would use both arm spans so that they could have a solar system scroll that is longer than 5 feet long. Or you can have them look up the height of an athlete, a scientist, a family member, or some other adult that is over 5 feet tall and measure out their particular height for this activity. Holding the roll of paper in one hand, stretch your arms out and cut or tear the paper at that length. Did you know that you just estimated your height as well? That's right. For the majority of people, arm span is directly proportional to height. Let's keep this relationship in mind as we move on. On the top of your scroll, where your head would be, write the word sun and mark it with a 0. On the opposite side, at your feet, label it Pluto or Kuiper Belt and also add a 1. We have now marked the center and the edge of our solar system. Now let's start folding and mapping our scroll. Start by folding the sun, or the 0, all the way down to the Kuiper Belt, Pluto, or 1, and folding our paper in half. Be sure to crease it, open it up, and mark the spot. Can you guess which planet is halfway between the sun and Pluto? Think back to what we learned earlier about your arm span is proportional to your height. What's halfway between your head and your feet? This is where the planet Uranus is. Go ahead and label it Uranus. I bet you'll never forget which planet is in the middle of our solar system. While most of what we are going to do today is simply folding in half, there are 2 special folds which we are going to fold in half and then half again. This next fold is the first of the 2. So go ahead and refold the scroll in half and then half again. Next, crease the edges and open it up. The scroll is now divided into quarters. Draw a line on the fold closest to Pluto. This represents Neptune's orbit. Draw a line on the fold closest to the Sun, and this represents Saturn's orbit. Now place the end of the scroll closest to the Sun at Saturn's orbit. Crease at the fold and open it up. Draw a line on this fold, and this is where Jupiter is located at. Fold the Sun into Jupiter, crease, and open it back up. This is where the asteroid is located. Now, the asteroid belt is really not this thin, but for air purposes, it's where we'll add the line in today's activity. Next up is Mars. Fold the Sun to the asteroid belt, crease it, open, and label it. Remember I told you that we'd make 2 special folds? Well, here's the second one. Fold the Sun to Mars, leave it folded, and then fold that section in half again. Make sure you crease it well. When you open it back up, you'll see 3 new folds. Draw a line for these 3 folds, one for each of the 3 planets closest to the Sun: Mercury, Venus, and Earth.
Wow, I just realized where space gets its name.
That's right. Many people are unaware of just how empty the outer solar system really is compared to how close, relatively speaking, the orbits of the inner planets are. So we've created a pocket solar system. And as we did that, we are highlighting Bode's Law. Bode's Law was developed in the 1970s before the discovery of Uranus, Neptune, Pluto, or the asteroid belt. This law is a mathematical way to describe the approximate spacing of the planets from our Sun. It's important to note that it is not a scientific law that works for all planets within our solar system, but it is helpful to understand how back in the 1970s they used this law to help find new planets within our solar system.
So you're telling me we can make our solar system just by folding in halves?
Surprisingly, it is pretty close. Now that we have the full scroll mapped out, let's take a closer look at these folds. In particular, the part-to-whole relationship, and see just how close these ratios really are. Think back to when we had the Sun as 0 and Pluto, or the Kuiper Belt, as 1. When we folded it in half, we found Uranus. So let's label Uranus as 1/2. And our first special fold was half of a half. That meant our line from Saturn was half the distance between the Sun and Uranus, or at 1/4 of our scroll length. And our line for Neptune was the fold that was halfway between Pluto and the Kuiper Belt and Uranus, or at 3/4 the length of our total scroll. Before we move forward, let's take a closer look at how we got 3/4 for Neptune. A common mistake may be to multiply 1/4 by 1/2, which equals 1/8, and then label Neptune as 1/8. Instead, we're adding the distance of 1/2 to 1/4. Remember that half is the same as 2/4, so the correct equation is 1/4 plus 2/4 equals 3/4. Then we fold it in half to find Jupiter, and half of a fourth is 1/8. So our line for Jupiter is 1/8 of our scroll length. Then we fold it half again for the asteroid belt, and half of 1/8 is 1/16. So our line for the asteroid belt is 1/16 of our scroll length. Then we fold it in half again for Mars, and 1/2 of 1/16 is 1/32. So our line for Mars is 1/32 of our scroll length. This point we made that second special fold. This is where we made half of a half. So the line in the very middle would be Venus, which would be half of 1/32 or 1/64. So our line for Venus is 1/64 of the scroll length. Then you have halfway between Venus and the Sun, which is our line for Mercury. And half of 1/64 would be 1/128, or 1/128. So our line for Mercury is 1/28 the length of our scroll. Now which planet is left? That's right, Earth. And so that last fold happens to be halfway between Venus and Mars. And that particular line for Earth is placed at 3/128, or 3/128.
That seems a little weird.
That's understandable. It can seem a little strange. But if we divide the scroll into 128 sections, we can make a little sense of all these different fractions. Let's go back to our first orbit, Pluto. Divided into 128 sections, Pluto's fraction is 128/128, and this can easily be simplified to 1. Secondly, Uranus was 64/128, just simplified to 1/2. Saturn is 32/128, or 1/4. Neptune, 96 over 128, or 3/4. Jupiter, 16 over 128, or 1/8. The asteroid belt is 8 over 128, or 1/16. Mars is 4 over 128, and that simplifies to 1/32. Mercury, 1 over 128, is already in its simplest form. Venus, 2 over 128, can be simplified to 1/64. Earth, at 3 over 128, is already in its most simplified form. So how does our solar system scroll line up to the planets and small bodies within our solar system? All of the fractions we just reviewed are pretty close to what scientists have observed. Well, here is a table that gives us the names of the planets and small bodies, and you can look at it in various different units. Average distance from the sun. Now remember, our planets are going in an elliptical pattern, so you have to choose a point with which to utilize for one set distance. So we look at the average distance from the sun, and that's called AU. You can also look at it in terms of miles. You can also create a solar system scroll that is about 13 feet long if you use 1 AU equals 10 centimeters, or you can also do the same one where 1 AU equals 3 inches. And from this, if we just take out and look at the scale in centimeters and inches, as well as AU, you can see our fraction equivalents from the scrolls that we created today. If you look at Pluto or the Kuiper Belt as being 1, if we were to round off 155 and say that's 160, well, what is 1/2 of 160? That's 80. Well, 75, that's about 80. Well, what's between 80 and 160? Well, it's going to be 120. Well, 3/4 there at 118. That's pretty close. Now let's go back and look at 75 inches. We said that was 80 at 1/2. What's half of 75? That's about 40. Well, 1/4 would be at 37. That's close to 40. Half of 40 is 20. Okay, 1/8, 20. There we are. And then if we were to look at the asteroid belt, and we put that in at 10 inches, that's about 1/16. And so, yeah, that would fall within the asteroid belt there. And so you can see as this kind of further breaks down how close this fractional equivalent really is to the entire scale of our solar system. So once you have this scale, the really cool part is that you can take and apply it to any known distance. So if you know the distance of your classroom, if you know the distance of your gym, if you know the distance of your state, we could do it for the distance across the United States. You can actually take the fractional equivalence, because a fraction is a ratio, part to whole, and do that for any known quality and set out a scale for our solar system. That's today's big idea about our solar system. We hope that you've enjoyed learning about scale and our solar system, as well as the comparisons that we've made between your own body and the objects within our solar system. Thank you for joining us today.
Thanks for watching this NASA STEM EPDC Quick Bit. Don't forget to check out the description below for more information and links.